Friday we looked at continuity. Basically, we just did the definition and some examples. So today we're going to do some theorems about continuity. This is kind of the third time we've done this. You remember for limits of sequences, we had a lecture where we gave the definition and then a lecture where we had a bunch of theorems. And then we did the same thing for limits of functions, and now it's the same thing for continuity. We don't have, our proofs are going to be very short. I think we've only got one actual proof today, because everything's going to follow from things we already proved about limits. So here's the stuff to remember from last time that I've written down already. You're continuous at a point if for every epsilon you can find some delta that makes that conditional true. So whenever the point is close enough to where you want to be continuous, then the function values are as close as you were told they had to be, which is epsilon. Okay. We made this note last time. It comes up here in just a few minutes, so I want to make it again. If you're looking at a point that's not a cluster point of your domain, continuity is free. There's really nothing to prove there. Because not being a cluster point means that for some value of delta, there's just no points that close. Okay? Other than the point itself. And the point itself is obviously going to satisfy the condition we want it to. Okay. Otherwise, if we're at a cluster point, then the quicker way to write this is just that the function at that point is equal to its limit as we approach that point. Okay. Now when we write that, as I've written over here on the right, we are implicitly assuming that that limit exists. Okay, so if the limit failed to exist, then you're just not continuous there. Okay, so to be continuous, you got to have a limit, and that limit's got to be equal to your function at that value if you're looking at a cluster point. Whereas if you're not looking at, if you're looking at a non-cluster point, it's just free. Okay. Any questions so far? I want to recall one more definition because we're going to use it today. I can't remember how much we stressed it last time, but this is also a definition to recall. Let A be a subset of the real numbers, and B a subset of A. Then the function f with domain A is continuous on B if it's continuous at all points of B. Okay. So there's not, there's really nothing to this definition, except I want to have it down because we're going to state some theorems in terms of this. Okay. Just a pedantic point, you'll notice that the preposition changes. We're continuous at a point, but we're continuous on a set. Okay. Any questions so far? In that case, let's move on to our first new material. This is essentially 5.2.1 in the textbook. get our hypotheses out of the way. A is a subset of the real numbers. F and G both have that domain. And they're both continuous at a point in there. And then we're just going to list some some functions that are also continuous there. Number one, the negative of f. I'm just copying the limit theorem. Number two, the absolute value of f. Number three, f plus g. Number four, f times g. And number five, again, copying the limit theorem. This is where we want to look at the reciprocal of f. Okay? And we are going to insist that f be non-zero on the entire domain. Okay, we'll talk about that in a second. So 1 over f is also continuous at a if f of x is not 0 over the entire domain. Any questions before we talk about the proof? So obviously, just like we did before, the f plus g and the minus f get you f minus g. The f times g and the 1 over f get you f over g if g is never 0. So any kind of operations you do, as long as you don't divide by 0, maintain continuity. Okay, the proof is really we just refer back to the previous chapter. Okay, there's one there's one case we need to think about, and that's that if A is not of cluster point of A, then we get continuity for free. Or, as we said back then, continuity is automatic. Alexis asks, can we use this theorem on the homework? Let me think about that for a second. Oh, no, you can't use this theorem on the homework. I should have phrased the second problem on the homework more carefully. I should have said on the second problem that I want you to do it from the definition. Okay. It's not like using the definition on the second problem of the homework takes very long. So Okay. Now, so we said that if A is not a cluster point, then there's really nothing to prove. If A is a cluster point, okay, then we can use the definition of continuity that you're continuous at A if f of A is equal to the limit as x approaches A of f of x. And we have a theorem that tells us that all these limits are going to work out. Okay. So if A is a cluster point, this follows from theorem 4.2.4. Okay, so let me just give you an example of how that follows. For example, if f of A equals the limit of f of x and g of A is the limit. So this is saying that they're both continuous there. Then f of A plus g of A is the limit of f of x plus g of x. Right? Is that okay? So there's really nothing to prove, and this gives us a bunch of stuff. So beforehand, we knew that like constant functions were continuous. We knew the function x was continuous. Well, now what can we do? We can do a bunch of things. In fact, sorry, we're going to do examples here in a minute after I make some comments. So let me make a couple comments. The first one is this reciprocal one. 1 over f if f is not 0 on its domain. Okay. This condition is a little bit harsh. Well, not a little bit harsh, I guess. But the point is, if f is continuous, then near any point where it's not 0, you can find a small neighborhood where it's never 0 on that small neighborhood. Okay, so you can always define it near any point that it's not 0. Okay. But, you think about it, this function 1 over f, that can't be actually defined anywhere where f is 0. So you might want to just restrict your domain before you do that. Second comment. We can replace at the point A with on the set A in this theorem. Okay, so instead of saying the following are continuous at A, we could say if f and g are both continuous on the entire set A, then the following functions are also continuous on the entire set A as well. This is actually theorem 5.2.2 in the textbook. Okay. I won't bother to write it down. Okay. Any questions before we move on to examples? Okay. In that case, do 5 examples 2 theorems and 4 more examples, I think, if we have time. Example 1. Polynomials. They are continuous on all. Every polynomial is continuous on the entire real line. Okay. Why is that? Well, polynomials are of the form that, and let's see, we proved that constants are continuous. We proved that the function x is continuous. So also the function x squared, that's x times x, that's continuous everywhere. X cubed is x times x squared, that's continuous everywhere. All the way up to x to the n, that's continuous everywhere. All these little constant functions, they're continuous everywhere, and so an times x to the n is continuous everywhere. And so we get to add them all together and be continuous everywhere. Okay. So it just follows from that theorem, just things we're allowed to do. Example B, rational functions. I don't know that that term has come up in this class, so let me just remind you. A rational function is a quotient of polynomials. Okay. These cannot be continuous on all of R. Well, I guess the trivial ones where q of x is a constant can be continuous on all of R. Otherwise, q is going to have some zeros. Okay. So let's take care of those. We know that q of x has a finite number of zeros. Why do we know that?
Because it's a polynomial.
Mm-hmm. Why do we know polynomials have a finite number of zeros?
I guess the max number of zeros would be the degree of the polynomial.
Yeah.
And so that's finite.
And we also just, reason graphically that, if it's like a well-defined function, you can only hit the x-axis so many times, or it doesn't work.
Yeah, I'm kind of asking, why do you guys know that all of that stuff's true?
Isn't this just known as the fundamental theorem of algebra?
Yep. It's the fundamental theorem of algebra. That's what I was. Oh, and Raphael has it in the chat. Yep. Okay. So we got to remove those zeros, right? Let A be the real numbers with those zeros removed. Well, then if we restrict to that domain, P of x is continuous and Q of x is continuous on that domain because we've removed its zeros. So then P of x over Q of x is continuous on A. And that's about the best you can hope for, because P of x over Q of x is not defined at any of the zeros of Q. Now, some of the zeros of Q might be removable singularities. That just comes down to, is the limit of your rational function finite? Well, I mean, does the limit exist at one of those zeros? If the limit exists at one of those zeros, then that is what's known as a removable singularity of your quotient. And you could define a new function that's also defined there. And it would also be continuous there, because you'd just be making it satisfy that second definition of continuity. Okay? These are all boring so far. This is more interesting, I think. Go ahead.
Yeah, so my question is, if Q of X has no real zeros, then wouldn't P of X over Q of X be fine everywhere?
Oh, I'm sorry. Yeah, I said something stupid. Yeah, I said it would only have no zeros if it's a constant, but of course it could have imaginary zeros. And then, yeah, then there's nothing to remove. Everything's fine. Okay. Now, what about sine x? We haven't. I don't think we've talked about the trig functions at all. I think we've been skipping everything. Today we have time, so I thought we'd talk about sine x. Why is that continuous? Or, I guess I should write down what we're claiming. It's continuous everywhere. But how would we prove it? Any suggestions? Don't look in the book to see how they prove it.
Maybe some squeeze theorem type proof, and using like the limit definition or the secondary definition of continuity.
Mm-hmm.
Is equal to its limit.
Yeah. Raphael has the question I was trying to get to. How do we even define sine? What is sine? Right? Since we haven't talked about sine, we haven't even defined it in this class. Okay? And we haven't made it to Taylor series, so we can't define it as equal to its Taylor series, like we would in complex analysis class. So we gotta say what we mean by sine first before we can even do this. Okay? I am going to say that sine is the function from the unit circle. The function sine and cosine are the functions which make the unit circle thing work. Let me show you what I mean. That's the unit circle. If we go a radians, then the point on the unit circle that we intersect is cosine A, comma, sine A. The x-coordinate is cosine A, the y-coordinate is sine A. Is it okay if I take that as the definition of the cosine and sine functions for us? For today? Any objections?
That's fine. Fine with me.
Okay. What's the arc length? Right here. Yeah, I'm on the unit circle though, Daniel. So that arc length is just A. Right? That's the nice thing about radians. Okay, that arc length is just A. Now let me go, let me look at sine x. I mean, I'm just going to draw another point on this circle and call it sine x, right? Let's say that that's x. And then this point is cosine x, sine x. That's that point. What is the arc length to that? Well, it's x. So here, our arc length is x. Okay? Now, what really are the sines? They're the y values. Okay? That's sine of A. And, I don't know, that is sine of x. With me so far? From this picture, we see the difference, absolute value of the difference between sine x and sine A, which is the distance you have to travel on the, here it's on the y-axis, to get from sine A to sine x. That distance is at most the difference of the arc lengths. Okay. The difference in the arc lengths is x minus A, absolute value. So if you traveled the arc length difference between the two, you'd go from your point A, but you'd be stuck along the unit circle. And you go to your point X. Whereas on the left-hand side, if you just want to, this is just on the y-axis, you would just start at wherever the projection of your point to the y-axis is, and you would just march up to the projection of your point sine x. People willing to believe me on this? I mean, you shouldn't just believe me. You should be convinced. Are there any questions about this?
Is there a way we could formulate this maybe more rigorously on paper?
I think it's...
I can't really think of how we would.
Yeah. You say rigorously, but I think what you really mean is algebraically.
That's the word, yeah.
But adding symbols, adding algebra, it doesn't make anything any more rigorous. Right? It just makes it look more like algebra. Okay. I think this argument is plenty rigorous.
I'm kind of confused as to like why is it clear that sine of x minus the distance between sine of x and sine of A is less than or equal to the distance between x and A? Because it's kind of hard for me to compare visually, like a curve and a straight line.
This is the distance from cosine A sine A to cosine x sine x along the unit circle. Okay, you start at one, you go to the other. I guess for the purposes of this discussion, let me assume that both A and X are between 0 and 2 pi, so that statement is strictly speaking true. This is the distance we were allowed to march just on the y-axis, so it's the distance from the y-axis projection of cosine A sine A to the y-axis projection of cosine x sine x.
Maybe if you want to compare straight lines to straight lines, you could think about it in stages. So if you take the point A and B along the curve, that length is going to be longer than connecting the 2 points directly. And then connecting the 2 points directly is longer than going on the y-axis. That's kind of how I'm thinking about it.
Yeah, I like
or
it.
Equal to or longer.
Yeah, I kind of see I see you're getting at the end. That helps. Thank you.
So Daniel's saying maybe should draw my axis first. If that's A and that's X, then the longest way you can get there, you can get from this point to this point, would be to walk along the circle. The quickest way would be to take the direct line segment. But then even better would be to just walk along the y-axis.
Right.
Oh, except that I drew the part of the y-axis I walked along was not quite right. You'd go from here to there. Okay. Now, if you want to do this algebraically, fine, look in the book. What do they use? They use the sine. Let's see. What do they do again? They use the sine of sine of x minus sine of a is equal to 2 sine of x minus a over 2 times cosine of x minus a over 2 x plus a over 2. See, I can't even remember what this thing is. Then they put the absolute values around. Okay, now that cosine term is at most 1. So we're there, right? And now they use the fact that sine x is at most x. I don't know. Why is that true? Well, if you ask me why it's true, I'd go back to the unit circle and I'd give you that explanation. Right? So we're back to my unit circle. But anyway, if you believe that sine of something is at most that thing, then we get the same inequality. Okay, but we got it a little bit more algebraically. Although again, how? I mean, for me, unit circle. Anyway, enough of that. We've got our inequality, which the one we wanted was this, and hopefully you see immediately that gives you continuity. Right? If you want sine x, let epsilon be given set delta equal to epsilon, right? If x minus a is less than delta, which is epsilon, then sine x minus sine a is less than or equal to x minus a absolute value, which is less than delta equals epsilon. There you go, there's your proof.
So this gives us from 0 to 2 pi. How would we extend that beyond? Because the picture gets messed up after that.
Yeah, okay, so
Well, I guess x minus a is its minimum if the x and a are within 2 pi of each other, and then the left side will be the same. So I guess it works.
Yeah, so my argument for that inequality with the unit circle, that argument only really holds for x and a between 0 and 2 pi. I agree. Now, one thing you can think about, if you want to generalize, I mean, that the inequality is true for all values of x and a. They don't have to be between 0 and 2 pi. So, if you really want to do the same argument, but for arbitrary x and a, you could do it on the helix instead. But then you're in 3 space. Remember the helix? The helix goes like that. And you can actually do it on the helix. And still, the absolute value, x minus a, would be the arc length between those 2 points. And then this would still be a smaller, in most, the inequality is still true because this would be projection onto the, still projection onto the y-axis, but projection in 3 space onto the y-axis. So if you really want to give a geometric argument, go to the helix. If you want to give more of an algebraic answer, say, well, I mean, if x and a differ by more than 2 pi, then if x and a differ by more than 2, then this is trivial, right? Because sine x minus sine a, that can be at most 2. And so if they differ by more than 2, you're done, right? Because the right-hand side is how much they differ by. Okay, so that's the more algebraic way to fix that. And then the other thing to notice is that we only wanted this to show that sine is continuous. Well, if you show that sine is continuous from 0 to 2 pi, then you can use its periodicity, and you've got it for the whole real line. Cool. Okay, I thought you guys were going to buy the geometric argument more than you did. I'm disappointed in myself. I'll have to practice how I explain that. Cosine. Well, would you believe it? Cosine satisfies the same thing. Not that. Satisfies the same inequality. Well, if you believe the geometric proof, you just go up here, and now instead of projecting onto the y-axis, we're projecting onto the x-axis. That's it. So it is quicker to just walk along the x-axis from the projection of one point to the other than to walk along the unit circle. If you want to do this algebraically, I don't know, there's some kind of angle addition identity that you might know, that I definitely don't know, that would do it for you. One assumes it's in the book. Okay. Any questions on that?
Could you scroll down a teeny bit? Your explanation is hidden under the menu bar. Thanks.
Pretty much just like graphically is that the projection is at most the actual point on the arc of the unit circle, which is why it just holds for sine and cosine. Whether the projection's on the x or y axis, it's always smaller than or
Yep.
smaller.
Yeah, so same reasoning, same geometric reasoning for both sine and cosine. And now we can do the others. Where they are defined, these are continuous. What are all the other trig functions? Tangent, Here, I'll ask for suggestions. What am I missing? What, there's some more trig functions? Ooh, let's give their full names. That'll be harder. Tangent,
Secant and cosecant.
secant,
You
cosecant.
have to take the zeros out first.
Yeah, so that's why I'm saying where they're defined. Because these aren't defined where their denominators are 0. And one more?
Cotangent?
Yeah.
What about the hyperbolic trig functions?
What's that? Yeah, hyperbolic trig functions are kind of trivial. Except we don't have the exponential function yet. Right? We haven't even defined e to the x. Once we do define e to the x, it's going to be immediately obvious that the hyperbolic trig functions are continuous. Right? Because what sinh x is, I'm trying to do that. Sinh x is, is it that? It's that up to some signs.
Yeah, I think that's it.
I should have done cosh x. That's easier because there's one fewer sign. All right. So as long as e to the x and e to the minus x are continuous, then sinh and cosh are continuous. Good.
What about the inverses of these on the restricted domains?
Yeah. So we haven't even. We're going to talk about inverse functions soon. Okay. But for now, we're not going to talk about inverse functions. Good.
Okay.
Yeah, sinh and cosh are useful for complex analysis too. Useful for a bunch of stuff. Here's a theorem. It follows from a limit theorem, so it's not all that exciting. But we should look at the hypotheses. The most interesting thing is the hypotheses. So A is a set, and F has domain A, and it's continuous at little a. If it's non-negative, then we can take its square root. So if it's greater than or equal to 0 for all points of the domain, then we can define this function. This is really the definition of a function that we would denote square root f, and it's defined by, for any point x, square root f of x is the square root of f of x. This is also continuous at the point a. Okay. Proof is exactly like the proof that we already skipped earlier. It just follows from limit theorems that we had. Okay. So now I want to get to our final result, the one we might actually prove, is composition of functions. Okay. So composition. Now what's the picture here? We've got one real line, another real line, and a third real line. F maps from the first one to the second, and then G maps from the second to the third. Now you've got some domain in here, that's the set A, and F is doing something to it. I don't know. Hey, let's shrink all of that to one single point. Okay, so f is doing something. We've got a point A that we want to follow. It gets mapped to a point f of A down here. And now G does something. G is defined on some domain B, and it does something to those points. Well, it's a single point. It's going to go to a single point. Okay. And now we can follow that point, f of A. That'll get mapped to G of f of A. Okay. Now, we want to say that this entire function, which is G circle f, this entire function is continuous. Now the entire function would be continuous at A, because the entire function goes from A to the real numbers. Okay? What are we going to need? Well, we're going to need f to be continuous at A. And then we're going to need G to be continuous at f of A. Okay. So let's state our theorem, and let's actually prove this one, I think. So this time we would have two domains. So f maps from A to R. So the domain of f is A, the domain of G is B. And furthermore, we need that the image of f is contained in the domain of G, because otherwise we're not going to be able to look at G of f. Okay? Now our hypothesis, if f is continuous at A and G is continuous at f of A, then G of f is continuous at A. Okay. Important to keep these straight. I think if you really think about what's going on and you draw a picture, it's going to be easy to keep them straight. But f, we want it to be continuous at the point A. G has to be continuous at f of A. But then the composition is then continuous back at the point A. Okay. Now, we've only got a couple minutes left. What I think I'll do is I will do a couple examples right now. And then we might as well prove this theorem. I'll prove the theorem after class, so if anybody has to go, you can catch it in the recording, or there's not much to the proof. So, okay, examples. Let me go over here to the side out, so we can come back to the statements. Okay, we did this in our first theorem today, but you can also do it as a composition. We know that the absolute value function is continuous, so if f is continuous, then anywhere f is continuous, the absolute value of f is continuous. B. Sine of 1 over x as long as 1 over x is continuous, which would be, by our previous theorem, as long as x isn't 0. This function, we haven't talked about it in class, but the book has a little bit. This has an essential singularity at the origin. So not only does it doesn't have a removable singularity at the origin, but it also doesn't have a pole. Okay. It's an interesting function. In any neighborhood of the origin, it takes on all the values from -1 to 1. And of course, we could also, any polynomial of sign. So if we want to be this way, we could also say sine squared plus cosine squared is continuous. And then you could actually use that trig identity and derive the fact that constant functions are continuous. That's completely ridiculous, so don't do that, but you could. Okay, well that's our time. Are there any questions? Like I said, I'm going to stick around to do the proof. If you have to go, I understand. No? You're all very quiet today. Okay. Proof, I'm just going to use the epsilon delta definition. So let epsilon be given. Because, what do we know? G is continuous at f of a. There is some. Now usually we'd use delta, but I'm going to want to use delta here in a minute. So we need a new Greek letter. I think gamma such that if, now what's the definition of continuity here? Now we're talking about G. So if x minus f of a is less than gamma, then g of x minus g of f of a is less than epsilon. Okay. So we're working backwards in this picture. We were given an epsilon, so that means we were given some neighborhood here of g of f of a. We want to get within that neighborhood. We used continuity of g to say, well, that means that we need to be in this neighborhood of f of a. And now we're just going to go back one more step. And we're going to say, oh, well, that means we need to be in this neighborhood of a. Okay. So, since f is continuous at a, there is some, now I'm going to use the delta, such that if x minus a is less than delta, then f of x minus f of a is less than gamma. And now I'll just write down the punchline here. Therefore, if x minus a is less than delta, then what do we know? F of x minus f of a is less than gamma. So now I'm gonna apply g. These points are within gamma of each other, or I guess I should say f of x is within gamma of f of a. So therefore, g of f of x is within epsilon of g of f of a. So my conclusion. And what did I do? I started with an epsilon and I got a delta. So we satisfied the definition.
And what about the g of x and g of x minus g of f of a? That was replaced by g of f of x, correct?
So we had some x's up here. They got replaced by an f of x later in the proof. Is that what you're asking about?
I believe that's the question, yeah, because I was actually talking about that same thing.
Yeah, I was actually, good. I was actually going to point this out after we brought the proof. We could have used different variables, but I'm going to highlight all the x's. But there's no need to, because x is just some dummy variable. Does that make sense? I mean, x is just, it's never defined to be anything. So there's actually no point to use a different variable. Again, the word I would use is dummy variable. But if you did want to, what would you do? You'd go down here and you'd say, you'd probably make the first ones y's. That would be the best way. You make the first ones y's, the second ones are all x's. Right, and so now what you're doing here is you're setting y equal f of x.
Couldn't we also just state what sets x is contained in? So in the first sentence, we could say that x is contained in B, and we specify that we're using x again. In the second sentence, we say it's contained in A.
We probably should have done this anyway. Well, now that I've switched it to y, if y is in B and y satisfies that, blah, 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 and then we would put in here, if, oops, I already have the if, x is in A, and, yeah, they're living in different sets, but reusing it isn't an issue because x never got a definition really. It was just a placeholder variable.
That makes sense.
Good. I mean, there's a much more technical way to say it, is that in each case where x occurred, it was bound. It was a bound variable, and therefore, outside of this sentence, well, I replaced x by y, but outside of the sentence, y has no meaning. Right? This is a statement about for all y something happens. For all y such that blah blah blah, then something happens. But anyway, I won't go into that. Oh, and I can